Hi there, folks. Professor G here. How you doing? Today we are going to talk about sedimentary rocks. We see the word lithification here, and this is a word that we discussed with the rock cycle, and it just means turning to stone. And I complained back then about how generic, or turning to rock, turning to stone, lithify, how generic the term was. And now we're taking that generic term and we're going to explain not only how sedimentary rocks lithify, but a couple ways that sedimentary rocks can lithify. And for what it's worth, we already talked about how igneous rocks lithify. If you recall, what does magma or lava have to do in order to become a rock? Hopefully the words cool and crystallize came to mind. All right, so that is the lithification process for igneous. Eventually we'll get to metamorphic rocks, and you'll hear what they have to do. When we talk about sedimentary rocks, we have to remember that there are three kinds of them. Okay, we've got clastic sedimentary rocks, we've got chemical sedimentary rocks, and we've got organic sedimentary rocks. And I'm not sure, I don't recall how much we went into them in the rock cycle, if at all. And it doesn't look like I have a slide right here, so it might do with a little bit of introduction before we go too much further. Clastic sedimentary rocks are rocks that are made up of all the rubble that's just lying around at the surface of the earth, anywhere from grains of silt and clay, very, very small stuff, to sand, to pebbles, to cobbles, bigger things, okay? Squeezed together, glued together, and presented to you as a new rock. I always joke that these clastic sedimentary rocks are the chicken McNuggets of the rock world. Okay, they're just pieces, parts glued together and presented to you as a new rock. Chemical sedimentary rocks are pretty neat. They form in water, and they grow crystal by crystal, almost kind of like igneous rocks too. We'll talk about these in some depth. Organic sedimentary rocks are a lot like the clastics in that they're just pieces of leftover stuff. But as the name implies, there's a decent amount of organic material included in this case. It's not just inorganic sand, silt, clay kind of stuff. It could be leaf material, seashells, a variety of things that we'll talk about. So clastic and organic are similar, and chemical is a totally different beast. So, talking about sedimentary rocks, it might be a good idea to say, hey, what the heck is a sediment? Sediment can be, all right, and typically what you think of when you think of sediments are weathered materials. Now, again, weathering is a term we introduced a while ago, certainly worth refreshing your memory. Weathering is the breaking down of materials at the surface of the earth. All right, weathering breaks things down. So you take a big rock, you make it into smaller pieces of rock. And how do we do that? Well, guess what? There's a whole chapter about that. So sediments are also materials that precipitate out of solution, or minerals that grow, excuse me, grow in solution. I just talked about chemical sedimentary rocks and how they grow crystal by crystal. Okay, we call those sediments as well. Sorry, I got a little bit of frog in my throat this morning. All right. Sediments can also be inorganic or organic. Okay. Inorganic is basically just this rocks and minerals and whatnot lying around at the surface. Organics, that means the material was previously alive. And I actually talked about this a moment or two ago. Seashell fragments, plant material, so on and so forth. Why did I separate inorganic out again here? Mineral crystals precipitated out of water. Okay, I guess a little foreshadowing here. When we get to chemical sedimentary rocks, people sometimes get confused because in some of the cases, like when we make limestone, we start with seashells. We dissolve those seashells into the water, and for a handful of reasons, the calcite that the seashells were made of comes back out of solution. That's what precipitating means. Remember the word precipitating a moment ago? They come back out of solution, and coming out of solution is the opposite of dissolving, by the way. Throwing a little chemistry at you here, I apologize. Just a little bit. So people get confused then. They're like, okay, well, you started with seashells, so isn't that organic? No. All right. Once something dissolves, you enter the realm of chemistry, and it's when it reprecipitates, it's all inorganic at that point. So this last bullet right here, this applies specifically to the chemical sedimentary rocks. But up here, okay, when we talk about organic material, if you look at the rock, you could see this material for the most part. It's not really evident in coal, for example, that it used to be plant material, but yeah, I don't want to get ahead of myself. Okay, so did have a slide, but like I said, it was kind of far off from where we needed it to. So one more time, here's what clastic sedimentary rocks are. Two examples, sandstone and shale. Very common examples. Everyone has seen these, whether you knew what they were at the time or not. Very, very common rocks. So to make these, it's a combination, it's a two-step process. It's a combination of compaction and cementation. You squeeze them and you glue them. Okay, squeeze them and glue them. And compaction is important because it reduces pore space. It helps the rocks hold together a little better. And the pressure typically comes from above, just from the rocks, the rock fragments being piled up on one another. The weight of the material above just squeezes it down. Then groundwater is always flowing through sediment, and it leaves a little residue behind. Okay, depending on where the water has come from, the residue might vary. Calcite, silica, iron oxide are all common cements. If water flowed through some limestone, it might have dissolved some calcite out. If water flowed through some sandstone or similar, it might have dissolved some silica out. Iron oxide could come from anywhere. So that gets dissolved into the water, and then as it flows through new material, it gets left behind, kind of like a little slime coat, if you would. Well, over time, just like you may have heard of pipes clogging up or something like that, over time the pore spaces clog up. They fill up with that residual cement. And at some point when the water can no longer flow through it, the material dries up and hardens. So two-step process to forming clastic sedimentary rocks. A clast, by the way, is just another name for a rock fragment. I guess we didn't really discuss that. And I use the word sand, silt, clay, pebble. Those are all clast sizes. You'll hear about those more in the weathering and erosion chapter. But so clastic sedimentary rocks are formed of clasts, which are different size rock fragments. All right. Organic sedimentary rocks. Rocks that form from the accumulated remains of organisms or plants. We still need compaction in this case, but we don't always need cement, depending on the amount of organic material included, um, you don't necessarily need to have groundwater flowing through.
Hi.
And sorry about that, my daughter came down. So as I was saying, you don't necessarily need cement because organic material is sticky enough on its own, and when it dries out, it can act as a glue. But you certainly could have groundwater flowing through additionally. So, all right, now we need to slow down a little bit. Why don't I give you examples here? I should give you some examples of organic sedimentary rocks. We gave you CLASTIC examples. So we're going to give you, let's actually add that here. Or was it on the previous slide? Yeah, let's put it here. All right, one rock you're definitely familiar with. If I could spell. This one you haven't really heard of probably, but there. Bituminous coal, which is just coal probably in your mind, and coquina. Okay, coquina is the seashell rock. It's very cool when you see it in lab. All right, so chemical sedimentary rocks, and here we go. We've got some examples. Limestone is a big one we're going to talk about, and halite as well. Halite is a rock that gets it's a neat way that it forms. So I see we're approaching our 12-minute mark here. I'm actually going to pause the recorder, and we'll start up our second segment. Alrighty, folks, and we're back. We're talking about chemical sedimentary rocks now, and I told you these were the kind of sedimentary rocks that grow in water crystal by crystal. So we got some words here that make some people nervous here. We see precipitation, we see solution. We're not talking about rain here for precipitation, okay? Precipitate is the opposite of dissolving, okay? And for those of you that know your chemistry, forgive me, I tend to oversimplify things for the folks that don't have the chemistry background, almost to the point of a little bit of chemistry heresy here and there. Please forgive me, but it works for most folks, and just quietly flinch when I say something that's inappropriate about chemistry. Anyhow, so precipitation is the opposite of dissolving. Everyone knows what dissolving means. Now we're going to tell you that dissolving is synonymous with going into solution. So coming out of solution is precipitating. All right, so they're deposited, which means they're put down, they grow by precipitation of minerals out of solution. A solution is water plus something dissolved in it. And two examples are halite and limestone, and we'll talk about how they both are a little different. All right, so let's see. Sediments crystallize, minerals coming out of solution, precipitating. Minerals were previously dissolved into water. We pretty much said all this. How did the minerals get dissolved in water? Well, that water flowed through a different rock and dissolved some of the rock around it. Okay. Water is the universal solvent. You may have heard that. Water will dissolve just about anything given enough time. It's much better at dissolving softer rocks, like sedimentary rocks, to be honest. It will eventually, if it sits in a bunch of igneous rocks, like you've got a giant vein of water, a giant crack in some granite, and it's all filled up with water, all right, the water will eventually start to dissolve away that granite. But if that were, say, limestone or sandstone, and the water was sitting in there, it would dissolve it a lot quicker. But anywho, so that's where the minerals come from. The water had flowed through some other material. Okay, now we need to talk about a term called oversaturation. All right. To saturate something means to, it cannot hold any more of anything. Um, you may not have ever said this, but let's say you get out of your car, it's pouring down rain, and you've got to go into a store or go to class, and you're absolutely soaked. You don't have a raincoat, umbrella, so you dash across the parking lot. But by the time you get to the door, you're dripping wet. Okay, um, and you say, "Ugh, I'm absolutely saturated." Okay. In other words, you cannot hold any more water. And the fact that you're dripping is probably a good indication of that because your clothes will absorb as much water as they can, right? And then at some point they could hold no more water and you start to drip everywhere. So saturated means you can't hold anything more. We need to think of a limiter here, just again for a moment. Environmentally, it's a little different, but let's just talk about a cup of water. Okay, a cup of water can only hold so much salt or hot cocoa mix or whatever. In other words, when you put the spoonfuls in, you stir it up, it dissolves. It's only going to take so much. And I use hot cocoa a lot as an explanation for here. Think about the packets of Swiss Miss. Nowadays, everything's in these individual little packets, but back in the days when you had those canisters and the scoops, right? And as I said, think about it. If Swiss Miss Company could have said, put in 23 scoops of hot cocoa, they would have told you that because, whoa, they'd sell a whole lot more cocoa if that were the case. But as it turns out, you could only dissolve one scoop of cocoa into 1 cup of water. It just won't hold anymore. And we've all done this. You try to make it a little extra chocolatier, and all you do is you get that sludge, right? Whether it's at the bottom or you get the little floaters on top. No matter what you do, that stuff just won't dissolve. So every mineral or every substance has a number of how much can be dissolved into so much water. All right. So we're not talking about hot cocoa. We're talking about rocks. So we talked about calcite from limestone. We talked about halite in rock salt, and as those are two common chemical sedimentary rocks. So what we're saying is that X amount of water can only hold Y amount of calcite. Okay? All right. So what happens is that two things. Okay? You either have too much waiting to be dissolved, too much calcite waiting to be dissolved, or you have that perfect mixture already and the water evaporates, throwing that side of the equation off. All right, we fiddled with putting too much in with the hot cocoa example. You follow? But now we're saying you made the perfect cup, but for some reason your water is evaporating out of your mug, and now it's throwing off your perfect equation. So what we call that when you throw that equation off is oversaturation. There's more stuff there than can be dissolved. And here's the funky thing. All right, here we go. Evaporation of water and over dissolving. Here's the funky thing about it is that water has such a strong desire to dissolve. And I know I'm anthropomorphizing it here, but giving water feelings, but it's just, it has to dissolve, okay? That it will actually spit out stuff that it has previously dissolved in order to keep dissolving new stuff. If it's sitting there waiting, the water will spit out what it dissolved in order to dissolve this new stuff. That's called precipitation. That's this oversaturation that I'm talking about. There's this brief instant where I guess you would say it dissolves first and then spits out to make room for it. I guess the way I presented it, it spits out and then dissolves. What really happens, and that's what pushes us into this oversaturation realm here, okay, is it dissolves this extra stuff, says, whoa, hey, I don't have room for that. Let's spit out something that we already dissolved. That comes out as a precipitate. That is our crystal of calcite that we just grew. So what are we dissolving? All right. The easiest example, again, we gave you was limestone, and we've indicated a couple times that limestone comes from seashells. Alrighty, so all right, we want to talk first about precipitation due to evaporation. This is our example for rock salt or halite. Okay, and we're going to talk about Salt Lake in Utah. With precipitation due to evaporation, we're going to assume that we had water at the perfect balance, the equilibrium, if you would. Okay, you had that perfect mixture of hot cocoa made, as I said a couple minutes ago, and the for whatever weird scenario you could come up with, you had to abandon your hot cocoa for a little while. Slowly but surely, the water evaporated out of it. Okay. Well, in nature, it's fairly easy to do. You just need to have a lake that has more evaporation output, in other words, than it has input, okay, from rain or snow melt or whatever. And over time, this lake will slowly but surely shrink. So the volume of water in there is reducing, reducing, reducing. So therefore, the amount of anything that's dissolved into it will slowly reduce as well. So in the case of Salt Lake, what's happened over the several thousand years is the lake has been shrinking and leaving these giant salt deposits around the lake. You've heard of the salt flats, right? They broke the land speed record out there a long time ago. It's an interesting place to visit. Very hard, dry, desolate looking place, but rather cool. And it circles, these salt flats circle the lake kind of like a rings on a bullseye. It's very cool. So anyhow, short story long, all right, as the water evaporates, the amount of salt that's able to be held in solution is reduced, and at a certain point, it deposits it. The lake continues to evaporate, makes another deposit, and what we're really seeing with these concentric rings around Salt Lake are the old shorelines. So pretty neat. Okay, this is the one that I talked about already, I guess, when we talked about the hot cocoa. Okay, you put in way more hot chocolate than you could possibly dissolve, and in this case, we've got seashells. Let's say that there is a massive algal bloom for some reason. All right. We won't even have humans causing this one. We've had algal blooms for millennia before we got involved with dumping fertilizers and whatnot into our lakes. But for some reason, the algae bloomed. It used up a lot of the oxygen, which killed off a lot of the seashelly critters. So you get a whole bunch of clams and snails and whatnot die, fall to the bottom of the lake or the ocean, whatever you want here, and slowly but surely their shells start to dissolve. All right, and you can actually see this when you look at the slab of fossiliferous limestone. Okay, you've got these layers of seashells and limestone deposited, and they're all just intermixed with one another. So the shells are dissolving, going into solution, and at some point, you're going to dissolve as much calcium carbonate, calcite, into that water as it can hold. But there's so many seashells left. It says, "Oh boy, I got to keep dissolving these guys." So it dissolves, it spits out, dissolves, it spits out, dissolves, it spits out. So you get this constant process going on. Okay, talked about that. The precipitation makes room for more dissolving. All right, so Um, that's basically it, and kind of why I stopped the previous video right when we got to chemical sedimentary rocks. I knew it would take up pretty much the rest of the lecture there. Just want to review that we told you about lithification of the three main types of sedimentary rocks: the clastics, the chemicals, the organics, and we gave you examples of each type of rock. Okay, and I'd like you to know these processes. Um, I don't give essay questions, but in some multiple choice sort of format, we want you to know what process results in what rock type. Okay, or so how do you get a sandstone or a shale? How do you get a coquina or a coal? Or how do you get a limestone or a halite? Alrighty, folks, take care.